gonna stay quiet for a little bit, and I'll allow you to just try to figure this out by yourself. And then we'll talk.
Should you also copy this table?
Yes, you will most likely need to reference this table again anyway, so. You are allowed a calculator, so. I don't have an answer if they did what I have on the board.
80. Yeah, 80. 80.
On the dot, 80?
Did you get 82?
Yeah, but he did.
Okay, guys, we had a situation like this yesterday, so I'll repeat what I said to you. It's important that you have that table. The table is going to be used for certain parts of the question, but what they often do is then they switch it up and they tell you this equation models what's in the table. This is called modeling. Alright, so it's not like the table values are unnecessary here. Like they're there, but we're just making a curve that fits those points. Alright, so that's what they are speaking about. So basically you don't use the table but realize that it's still there, and then you go ahead and you answer that question. And sometimes they don't give you the units, they say just find the average number, and then they try to figure out if you know how to tell what the final units are going to be as well. Okay, please pay very careful attention to this discussion. The second FTC is a really confusing theorem. If you thought that the first FTC was manageable, this one is definitely harder. If you thought the first FTC was pretty bewildering, this one is even more so. Okay. So yes, you have this. That was an initial kind of snapshot at it. Okay, now, the first thing I want to do is just kind of tell you where does this stand with everything else. All right. Look, the first FTC. Just kind of look at the colors here. What it used to do is it would actually integrate, right? It would integrate a derivative. That's what its job is for it to do. And then of course when you rewrite it, it does other things for you, but it's still born out of the same concept of an integral of a derivative, okay? So what happens in the second fundamental theorem is we actually are taking a derivative of an integral. Now anyone who can connect the dots will be like, well, this doesn't seem too difficult, I'll just go ahead and integrate first, and then I'll go ahead and I'll take a derivative. But they will almost always give you a function that you can't integrate. You don't have the skills or the know-how to integrate it. So you're stuck with figuring out, okay, how do I take a derivative of something I don't even know how to integrate, all right? So we basically have reversed the direction from the first FTC saying that you're gonna take an integral of a derivative. Now we're saying you're gonna take a derivative of an integral, and usually it's an integral that you wouldn't be able to evaluate by hand, okay? So, what do you do then if you can't evaluate these integrals by hand? The second FTC says that whenever you're asked to take a derivative, the other day when I put this, I put it for you in color, but today I'm against time a little bit. Whatever that function is, all right, the first thing you want to jot down is don't actually integrate it, because I can tell you right now, you're gonna see a question like this and you're gonna be tempted to start integrating the question and then thereafter taking a derivative. That's what pretty much everybody does. And sometimes I ask you to do that to prove it to yourself. I think that's the homework is like that too. So write down, don't actually, I'm writing this for you very informally, integrate this.
Is there ever times where it does work?
It will always work.
Or that you know how to do?
Yeah, right, of course, unless you are asked. And by asked is, in the homework, it's gonna say, prove that the second FTC works, okay? So you're actually gonna integrate it and take its derivative and stuff like that. So really, the second FTC, I actually didn't even know such a thing existed until I started teaching, because my teacher never told me this was true. So I used to actually sit there integrating things and then take the derivative later and be like, wow, that took forever. But this is basically, the second FTC is more or less a shortcut to the process of integrating first and then taking a derivative. So it says the following. It says step number one, you're gonna go ahead and you're gonna evaluate the function at u. Again, not the integral, nor the derivative, but the actual function that you see there. You're gonna go ahead and you're gonna throw u into that, all right? And the second step, which is often forgotten, is you're gonna take a derivative of that over there, of that expression, so times u prime. So if you guys notice, this sounds a lot like the chain rule, okay? So it is pretty much an application of the chain rule, but I don't wanna get into how that is, because it's not really gonna help the discussion right now, okay? I really just want you to learn that shortcut quite well. If the formula is bothering you, I wrote this book a long time ago at a time where literacy was very low in Salam school, so I used to write everything down in steps for them. So some of this stuff is really not necessary for most students. But if you feel like you're losing track of the formula, I've written it into 3 simple steps. Find the function at u, find the u derivative, and then just basically multiply the two, and that'll get the job done, okay? Up until a few years ago, some of these slides were totally necessary to mention to students. Now it's not as much. You'll notice that this sounds a lot like the chain rule too, okay? Yes? Yeah. All right. So let's go ahead and practice some. Go ahead and copy down both of these problems. They're basically one-liners. So if you've been listening really carefully, you can probably just do this by yourself if you understand what the formula is designed to do. So first thing you have to recognize, they're asking me to take a derivative of an integral. If you just say that to yourself a few times, you'll know that this is, see, nowhere does it use the second FTC, right? You just kind of have to realize that the way this is ordered, this must be the second FTC. So step number 1, take this x over here and plug it into this function, just like you used to plug things into functions in pre-calculus, all right? So that's basically your function evaluated at u. And so you guys will notice that that's going to essentially look like the square root of x squared plus 1. Now here's where this kind of departs from the chain rule. If you guys recall the chain rule, the way it was designed is you would take a derivative of the inside like this, but that's not quite what they're designed to do. What you really need to do is you have to go back to this and take its derivative. So what's the derivative of x that I'm going to multiply? All right, so make sure you write that out explicitly because it's not always going to be 1, okay? And that's it. That's the end of the second FTC. Your final answer is basically going to be the square root of x squared plus 1. So go ahead and do the next one by yourself. I'm going to quietly do it on the board here. Guys, how are we doing? Yes, no? Now, it's a good idea to, simplify a little bit. It's a good idea to take this piece right here. See, I purposefully put it there because that's how I'm teaching it to you. But it's always a good idea to take that and put it before the square root. Okay, usually that ends up happening in some weird way. So, in my final answer, I'm actually going to write down the term right over here, 8x cubed. And then, as Mason just said, you should probably simplify that a little bit. So 2x to the power of 4 squared, how much does that give you?
4x to the power of 8.
4x to the power of 8. So that would be it. Now please don't make any other forms of algebra. Usually they'll give you something that if you're weak with algebra, you'll be like, oh, can I take a square root of those and make it like 2x to the power of 4 plus 1 or something like that. So none of that is true. Algebraically, it's just not true. Okay, here's the other way that they can express this to you, and I think this is the trickiest one, where they don't write it the way that I had the first two examples written. They actually write out for you, find the derivative of, and then they write for you an integral. So the integral is f of x, and notice how that's a big F, that's not a small f. The integration from pi over 2 all the way to x cubed cosine t dt. So, I don't know who said this, Mason said it or somebody said it. See, in this scenario, you technically could integrate that. Do you guys know how to integrate cosine? You do, right? You could actually integrate that. And then you could take the derivative of what you got, but again, that's not what the question is designed for, okay? So realize this is actually trying to get you to use the second FTC. This is straight off of the AP exam. So the way you're supposed to do this is you're supposed to write down that what this means is d dx, so the derivative of, the integral of, pi over 2, x cubed, cosine t dt. And again, stick to the same two steps. No matter how easy it looks like, you can integrate this. That's not what the second FTC says. So you go ahead and you take the cosine t, and you plug in x cubed into it. And what do we multiply all of this by? I have a quick question for you. Does it look like the number on the bottom ever seems to matter? No, it does not. Make a note of that, please. Alright. It doesn't matter what that is. Okay, so if you're wondering why is that true, it's because think back to derivatives and derivatives of constants. What's the derivative of any constant always going to give you? A 0. That's why it doesn't matter. Okay, because remember the whole process is about taking a derivative of an integral. So you would technically have integrated this first and then take a derivative, but you see it doesn't matter because the derivative of a constant would just be 0 then. Okay, so this is again a second way that they've expressed this. All right, go ahead and try this one. This one is sort of similar to the previous example, except it's got more notation involved in it. And I think this is perhaps the most popular way that they express this. Please make sure you write down what the question says. Like the words there are really, really important. And if you write it down, go ahead, give it a shot. Do it by yourself, inshallah. Guys, what did you get as an answer to this question?
X has X prime.
And what is x prime? 1, right? So it's simply equal to what then? X. Okay. This leads to the most common and repeated question on a free response on the AP exam, okay? So jot these things down. Guys, this right here is called the accumulation function. Alright? Just like you guys have linear functions and square functions, calc has its own names for functions. This is called the accumulation function. Why do you think they would call this that particular name? Why would they call it an accumulation function? Give you a big hint. Think about what is the purpose of integration anyway? It finds area, right? So why would they call it accumulation function?
Because the higher the X goes, the more area you're covering.
There it is. Okay, look. Let's suppose it's snowing outside. Okay, let's suppose it's snowing outside, and I'm interested in knowing how much snow has literally accumulated in the last, I don't know, hour. I'll just go over here and I'll say I am interested in the g of 1, and automatically that x will turn into a 1. So I'll be able to tell how much has accumulated in the first hour. I'm like, you know what? I'm not interested in that anymore. I'm interested in hour 2. Well, I change that, this changes automatically. You see, that one is already grounded. It's not ever going to change. So this is why we call this the accumulation function. You keep changing the x, that's going to also change the area. It's going to tell you how much more you're picking up along the way. Okay, so that's fact number 1. This is actually fact number 2. Whenever you take a derivative of an accumulation function, what ends up happening is it's actually equal to the function that was on the inside. So g derivative is equal to f. So I like to tell students to think of these as modes, all right? The g function is in derivative mode, right? This is in derivative mode. That one is not in derivative mode. That is technically in function mode, all right? So one of them is always lagging behind the other. So whenever you are going to make conclusions about this function, you're just going to double up those conclusions about the derivative of some other function called g. But this goes a little bit further. What do you think would happen if you were asked to take a second derivative? Because this was derivative mode, and sometimes you want to tell concavity, so you decide to go into second derivative mode, which is, again, concavities. What would happen to the function on the other side? Like I said, it's one of them is lagging behind the other. So this other function, now it is in derivative mode, and more specifically, it's in first derivative mode. So fact number 1 is right over here. Fact number 2 is right over here. And fact number 3 is right over here. The reason why this makes its way into this lesson is because you need to know how to use the FTC in order to go from here all the way to now what's your number 2 right there, okay? We're gonna do a lot of problems in the coming week that is related to that. And so just leave that on your notebook. Let's do a few other things and then we'll wrap it up for today. So here's one of the more recent problems that has shown up on the AP exam. Go ahead and answer this one for me. Okay, so there's, no, this is non-calculator, okay? Remember, somebody who doesn't understand the second FTC is gonna actually try to integrate this, and soon you guys will actually learn how to integrate something like that, okay? That would be the next lesson down called Q substitution. So it's very misleading the way it's designed, but I want you to just mark down that this is still the second FTC because they're interested in not this function, but its derivative. So what would you guys say is the correct answer then?
D.
Alright, so the letter, is it C or is it D?
D.
Is D. Okay, that's it. Alright, two-step process. Take that X and plug it in, so it looks like this. And then don't forget that there's still a -1 there. And then go ahead and take a derivative of X and you end up with 1. Okay, they purposefully put that there to see if somebody would get misled and think that the one is.
Wait, why does the 1 stay?
Excuse me?
Why does the 1 stay?
Because that's the whole function. That's the whole function right there. So it needs to stay exactly as all of those stayed. They haven't removed anything from there. Okay? And do this last question. Set 3 is your homework for the weekend. It's not that long. I think you guys will be fine with it, inshallah. Today is 28 or 33? 33. Okay. Yet again, notice that this is a function that you technically do know how to integrate, alright? So you might be tempted to say, you know what, let me just go ahead and integrate this. And today you learned an easier technique to deal with this. You want to keep writing this down until it just settles in for you that whenever they do this, there's a way about it. Your answer should be the square root of x squared multiplied by 2x. But I doubt that answer is going to be there because what's the square root of x squared?
X.
And then what's x times 2x? So this is really the answer they most likely have at the board. What is that? Alright, so there you go. That's the second FTC. The harder part of this is, by the way, the pure response questions. That we'll get into next week. Okay? Alright then. You guys can relax.